In this session, we'll analyze line-to-line fault with a fault impedance. Once again, I'm considering unloaded generator on which the line-to-line fault occurs with a fault impedance of ZF. That is, the system to be analyzed is I'm showing here, that is unloaded generator with the fault that takes place on phase B and C with a fault impedance that you can see here, ZF. Then one you can observe here, that is the current IN is equal to 0 because the fault is not involved with the ground. The fault is not involved with the ground. Now the fault is occurring between B and C with a fault impedance of ZF. That's what I have shown here. For this, you have to write the boundary condition. That is, the first boundary condition is the current I is equal to 0. Current I is equal to 0. And another the condition we have got IB is equal to minus IC once again. And the third condition, you can look into here, the voltage here, the terminal voltage across phase B is VB and the across C is VC. That is, the voltage what we are getting here is VB and here it is VC. Therefore, there is a difference between VB and VC. There is a voltage drop, that is nothing but IB into ZF. Therefore, you can write the voltage condition as it is a VB minus VC is equal to IB into ZF. That is, there is a potential difference between this point and this point, that is IB into ZF. That is nothing but here it is a VB here and VC here, that is IB into ZF. The same the terminal conditions I am writing here, that is the boundary conditions are, the first one is VB minus VC is equal to IB into ZF. That is same thing. Here it is a VB, here it is a VC. There is a phase displacement, that is a potential difference from this point to this point, that is VB minus VC, that is equal to IB into ZF here. Then the next the condition is IA is equal to 0. Then IB is equal to minus IC. It is quite evident from this figure. That is IB and IC, they are equal and they are acting in the opposite direction. Therefore, it is IB into IC. Then you have to make use of the symmetrical component of the 0, positive and negative sequence currents. Just you have to substitute in that one. That is the condition what I have got is IB is equal to minus IC. That is a terminal condition 1. Then another one is I is equal to 0. If we are putting these conditions in our symmetrical components, that is what I am putting here is IA naught. IA naught is equation is 1 by 3 IA plus IB plus IC. The condition is that instead of IB I am replacing IC. IA is equal to 0 because I is equal to 0. Therefore, IA naught is equal to 0. Means it is quite evident from the figure itself, the nature of the fault itself, that is the fault is not involved with the ground. Therefore, the zero sequence current is 0. What I am getting here. Then you have to calculate the value of IA1. The value for IA1 is 1 by 3 IA plus AIB plus A square IC. Just you have to substitute the condition here, that is IA is equal to once again 0. IB is replaced by minus IC. Then IC is same as it is. What I am getting is 1 by 3 A square minus A into IC is the IA1. Similarly, we can calculate what is the IA2. IA2 is 1 by 3 IA plus A square IB plus AIC. Once again, put the terminal condition, that is IA is equal to 0, IB is equal to minus IC, and IC you are retaining as it is. Then if we are simplifying this, what I am getting is minus 1 by 3 A square minus IC. If you are looking into the magnitude of IA1 and IA2, they are the same, but they are acting opposite to each other. Therefore, you can come to conclusion that it is IA1 is equal to minus IA2 because it is 1 by 3 A square minus AIC. whereas this as minus 1 by 3 a square minus ic. Therefore, the first the relation between the the sequence currents I am establishing here, that is Ia naught is equal to 0 and Ia1 is equal to minus Ia2. Ia1 is equal to minus Ia2. Okay, just you have to make here, it is Ia2 minus Ia2. Just you have to write it very clearly. Okay, that is what I am getting here is Ia1 is equal to minus Ia2 very clearly. That is the one relation between the sequence current I am getting, set of the relation in Ia naught is 0, Ia1 is equal to minus Ia2. Next, I am considering here sequence voltages, that is VA naught, VA1 and the VA2. We know that VA naught is equal to minus Ia naught Z naught. We know that is Ia naught is 0, therefore the VA naught is 0. VA1 is EA1 minus IA1 Z1, that is I am retaining as it is. However, the VA2 is nothing but your minus IA2 Z2. This minus IA2 is replaced by plus IA1. It is replaced by IA1 because we are establishing the relation between the sequence current as IA0 is equal to 0, IA1 is equal to minus IA2. This minus IA2 is replaced by IA1. Therefore, VA2 is equal to, what I am getting is IA1 Z2. Then we know that the boundary condition, one boundary condition is VB minus VC is equal to IB into ZF. Just you go on substituting value of VB and VC in terms of sequence voltages, and whereas IB is also expressed in its sequence current. So that what relations we are getting, just you have to observe here. That is, I am putting for VB, that is VA naught, A square VA1, A VA2. This minus as it is here. Instead of VC, I am putting VA naught, A VA1, A square VA2. Then IB is replaced by IA naught, A square IA1, A IA2. The sum of the things you can observe here, VA naught is 0. Therefore, in the wherever there is a VA naught is there in this equation, that is equal to 0. Then the another condition is that the IA1 is replaced by minus IA2. That is already taken care in the sequence. That is IA naught is equal to 0. That here you can put IA naught is equal to 0. Okay. Now just you have to simplify this. What I am getting here. Here I got VA naught is equal to 0, A square VA1. Here it is A VA1. Therefore, I am clubbing a VA1. Therefore, VA1, if we are taking the common, here it is A square. Here it is minus sign, minus A VA1. Therefore, minus A VA1. Similarly, I am grouping the VA2 terms and I am getting A square minus A into VA2. Here it is A VA2, it is A square VA2 with a minus sign here. Just I am changing the sign by taking minus outside here, that is A square minus A VA2. Then the right hand side you can see here, it is A square IA1 plus A IA2. This A IA2 can be replaced, IA2 can be replaced by minus IA1. Therefore, I am replacing here, instead of A IA2, I am putting minus A IA2. A as it is, instead of IA2, I am putting minus IA1. Therefore, it is A minus A IA1. Further, if we are looking into here, A square minus A VA1, A square minus A VA2, A square minus A IA1 ZF. On either side, A square minus A is a common, that is get cancelled. Then ultimately, the relation what I am getting here is VA1 minus VA2 is equal to IA1 ZF. Then substitute the value of VA1 and VA2 from this equation, so that there is only one variable we are getting, that is in terms of IA1, so that I can calculate what is the value of IA1. Therefore, VA1 is A1 IA1 Z1, VA2 is IA1 Z2, IA1 Z2, that I am substituting as it is instead of VA2. Then IA1 ZF as it is. Here you can transfer IA1 Z1, IA1 Z2 to the right hand side, then calculate IA1, so that the value of the IA1 what I am getting here is EA divided by Z1 plus Z2 plus ZF. This is the value of IA1. Once I get the IA1, I can calculate what is the value of IA2. That is the minus of this. Minus IA1 is nothing but IA2. IA0 is 0. Then you can calculate what is the value of IB plus IC, that is IB, or minus IC, that is a fault current. That we'll look into here. The fault current is IB, that is IB is expressed as IA0 plus A square IA1 plus A IA2. IA0 is 0 already. Then A square, it is IA1, it is IA2 can be replaced by minus IA1, therefore it is minus A here, it is IA1. The value of IA1 is already you are calculated, that is it is A square minus A, EA IA1 is EA divided by Z1 plus Z2 plus ZF. This is where the fault current in the line to line fault with the fault impedance of ZF. Then one more important, the relations what we are established here is the value of the VA1 and VA2, that is VA1 minus VA2 is equal to VA1 minus VA2 is IA1 ZF. That is the difference between VA1 and VA2 is IA1 ZF. Means you have to connect the positive and negative sequence network in a such a way that is in between there is a difference between VA1 and VA2 should be IA1 ZF. That is, this you have to take care of. Therefore, I am drawing here the sequence networks, that is IA0 is equal to 0, IA1 is equal to minus IA2, and IA1 were calculated, and the fault current IB is A square minus A into EA divided by Z1 Z2. You can look into the sequence diagram here. This is the positive sequence network. This is negative sequence network. You have to join positive and negative sequence network in such a way that the difference between VA1 and VA2 should be IA1 into ZF. IA1 into ZF. Therefore, what I am doing, I am connecting here ZF. That is ZF. Then you can see here it is a VA1 here. Here it is a VA2. That is here it is also VA2. That is VA1 minus VA2 is equal to IA1 into ZF. This is how you have to analyze the line to line fault with the fault impedance.